Okay. Now the first unit actually it discussed the fermentation technology. And when we come to the fermentation technology, uh, fermentation, that term needs to be explained. The word fermentation from a microbiological perspective, if you address that term in a microbiological perspective, it is used to describe any biological process occurring under aerobic conditions or in the absence of oxygen. However, many researchers use this term to describe any process that uses a microorganism to convert a particular medium or a substrate into a product. So usually a fermentation where nowadays used broadly for application of a microorganism for the conversion of a product. But usually in microbiological terms, we had to take only the anaerobic processes done by microorganisms for a conversion of a product. But alternatively, there is another usage. People will generally use the term fermentation even for aerobic process also. Now, two important aspects of microbial growth, which are of prime importance in industrial microbiology or fermentation technology, is production of primary metabolites and secondary metabolites. And we can see that the primary metabolites are resulting from the log phase or trophophase. There's another alternative term that is used to describe the log phase, trophophase. And these primary metabolites were basically they're produced during the log phase or the trophophase, and the secondary metabolites were resulting or they're actually produced um, during the stationary phase, which is also known as the idiophase. So that's the basic difference in the production of primary and secondary metabolites. And some pathways were already displayed in the screen. You can see that the primary metabolites, for example, during the process of glycolysis and there is a crush of chorismate, tryptophan, tyrosine, phenylalanine, etc. were coming into the primary metabolism. And these primary metabolites were generally treated as essential components for the cell growth. So if a primary metabolite or the production of a primary metabolite fails, then cell may not be able to grow. And secondary metabolites were not that much required for the optimal maintenance of the cell or the growth of the cell, but they were produced only at a later stage, like stationary phase or idiophase. And we will be discussing that in detail later. In the fifth unit, we'll discuss the production of these primary and secondary metabolites and their regulation, etc., in detail. So, as I explained, the primary fermentation or primary metabolite production, it actually occurs during the log phase of growth or trophophase of the growth. So that means the increase in the biomass. From the first picture, you can see that here is the weight or biomass increase or cell number increase. Lag phase and log phase is shown here. And the product formation or the primary fermentation product formation follows almost the same pattern as that of that biomass increase. So that's the case of primary fermentation or primary metabolite production. Whereas in the case of a secondary metabolite production, we have the secondary metabolite like penicillin, which is produced during the stationary phase or idiophase. So its production starts at a later stage, not it starts with the production of biomass or increase in the cell number, and it only increases when or it reaches its optimal production only after the cell reaches its or the cell mass reaches its idiophase or stationary phase. So this is the basic difference between the primary and secondary metabolites. And as I mentioned, primary metabolites were actually more essential for growth and maintenance of the cell, whereas the secondary metabolites are not. They can be treated as a byproduct or something. And this is another picture which shows that there is a decline in the substrate concentration. So initially the media will have maximum 100% substrate concentration, but during the cell mass increase and primary metabolite production increase in the log phase, the substrates will be continuously utilized and it will decline. And by the time it reaches the stationary phase, there will be a shortage of the substrates. And that substrate shortage or that also induces the secondary metabolite production. So this is a phase or the ideal phase where the substrate is present at the minimal level is the optimal phase for the production of a secondary metabolite. Okay. Now we come to the different fermentation technologies. We have basically two types of fermentation process. One is a liquid fermentation and the second one is a solid state fermentation. The liquid fermentation is a controlled process which consists of growing cells in a broth medium or liquid medium. And in a bioreactor used for liquid fermentation, sterility of the materials can be maintained and controlled, and control of the temperature, pH, then dissolved oxygen, mixing, all these parameters can be arranged, and it is possible in a bioreactor. So it requires maintenance of sterility, maintenance of and control of the temperature, pH, dissolved oxygen, and even agitation or mixing. Everything needs to be controlled in a bioreactor, such a liquid fermentation bioreactor. And this will provide an optimal environment for the specific microorganism to grow. Liquid fermentation systems are of two types. One is the static and the second one is submerged. You may be already aware of this. Anyway, we are just recollecting the topic. So, static culture means in static liquid fermentation, there is no mixing. So, that's why it is called static. Whereas the submerged fermentation, there is a in submerged liquid fermentation, the liquid broth is mixed with so that a shaken flask in your laboratory can be considered as an example of a submerged fermentation. Whereas if you are just keeping the flask in your incubator, that's a static culture. Now, in solid state fermentation, the second type, it is this solid state fermentation is the aerobic growth of microorganisms on solid substrates under limited water conditions. So the microorganisms were growing on solid substrate as shown here, arranged here. The microbes were growing on solid substrates in the reactor, and also there is only limited water supply. So water limited conditions were there. The solid matrix which provides the structure to this material may consist of organic based materials like cereal grains, wood chips or compost, cheese, etc. Such supporting materials were used for supporting the growth of the organisms. Or inert materials like perlite or vermiculite, etc. Can be alternatively used. And they are and impregnated with, or they are actually supplied with the liquid nutrient broth, so that the reaction can be, or the microbial growth can be enhanced. So it will be supplied with the liquid nutrient broth in limited quantities. So here is a flowchart that shows the production of such products in a solid state bioreactor. Basically, we have a substrate which may be a bran or some cakes, etc., that can be used as a substrate, which needs some mechanical treatment like a pre-treatment with heat, etc. And such treatment requires energy, and the pre-treated substrate is then used in the reactor. This also supplied with the various forms of energy like mixing or aeration or then water, limited water supply, then inoculum, medium, etc. And such inputs will be given to this pre-treated substrate. So the solid fermentation, it also requires searing and aeration, which all demands supply of energy. And finally, you will have the fermentation products. And that fermentation products based on the solid state fermentation can be used in nutrition and human health, then animal feeds, various fields like biofuel production, then bioproduction of grains and crops. So in various or diverse fields, we have a direct application of such solid state bioreactors. So this is an example of a solid state fermentation. Okay. Now we'll come to the different steps in the fermentation. Is there any questions regarding the previous sessions?
No, sir.
Okay. Now, in the different steps of fermentation, the first step is fermenter selection. You have to decide which type of fermenter that you want to use based on your desired application. And the second one, or second critical component, is the microbial strain that is used in the reactor. So you have to select the microbial strain. And then you need a fermentation media. Optimal fermentation media is almost important, and as that of the strain, because the strain requires specific fermentation media or optimal fermentation media, which needs to be optimized using various protocols. Then fermentation process. You need a better understanding of the fermentation process, so that maximum output of that product can be produced by controlling the different parameters. So that demands the better understanding of the metabolic pathways in which is involved in that reaction, so that you can minimize the production of unwanted products and enhance the or maximize the production of the concerned desired product, which also enables you to minimize the impurities that demands separation in the later stage. So a better understanding of the fermentation product will help you to design the fermenter in such a way that your fermentation product or desired product will be maximally produced by regulating the metabolic pathways. And we will discuss that process or the regulation of the fermentation process in the fifth unit, where we discuss the primary and secondary metabolite production and its regulation. Okay. Now there is upstream processing and downstream processing. You all are already familiar with the terms. Then there is a quality control and assurance methods, which was also required in an industrial fermentation, product recovery, packaging, etc. So there are various stages in the industrial fermentation process. Now, when we design a bioreactor, an optimal bioreactor, we need to consider that's the first step. The selection of the bioreactor is the first step. So there we require different parameters to be considered. The bioreactors can be classified according to various different criteria. So, for example, a type and form of the biocatalyst. That's one criteria. So, free cells in submerged cultures, then carried or bound or immobilized enzymes, then retention or recirculation of the catalyst. So, etc. That means, for example, if you have a free cell as a biocatalyst, then you will use a submerged culture system where you can easily grow the cells and agitate. So free cells like yeast cells in a broth medium, in a shaken flask, or as or a continuously stirred bioreactor. Then the optimal use of that free cell is in such a submerged culture system. Okay. Now, bound or immobilized cells. In that case, we need some retention or recirculation biocatalyst. For example, an immobilized system, where the cells will be fixed onto some solid substrate, some microcarrier beads, or some hollow fibers, or some other inert materials, or some packing beds. So wherever some solid support is available, you can bound the cells, and which will enable you to enable the retention of the biocatalyst and also recirculation and reuse of that biocatalyst, which is not possible for a free cell system, submerged system, because once the product is extracted from the medium after the fermentation, the cells will be discarded in such a submerged system. Whereas immobilized systems or other systems in which the cell types were all the biocatalysts or the cells or enzymes were fixed or immobilized onto a support material, then you can recirculate and recycle such biocatalysts. So based on which cell type you are using, you require to select the proper bioreactor and the method of fermentation. So you have to select whether a submerged system or a immobilized system. Which one you need to use, that is dependent upon the cell type that you are using. Another configuration of the tank. The tank or the reactor reactor vessel. Usually a height diameter ratio that should be less than 3. So the column height and diameter should be, in a column reactor, the height diameter should be greater than 3. So usually there are two types of configurations where we can say that there's a tank reactor and a column reactor. The column in the tank reactor, the height diameter time that proportion should be less than 3. That means it will be wider. Whereas in a column type, it will be longer, or the height will be more. So that diameter will be that ratio will be greater than 3. Okay. Now, energy input and aeration, that's another criteria, where you can use liquid phase or gas phase or a combined method of liquid and gas. So various types of energy inputs, like for mixing and aeration, you can use various methods. And that is possible with airlift reactors, for example, in the gas phase. Or you can use another liquid phase reactors in which you can give some mixing and agitation, etc. So that type of reactors where energy input is required, either in the form of agitation or aeration, is another criteria. Then hydrodynamics means perfect mixing or partial mixing or no mixing. What type of mixing is required? So that needs to be considered. Some cells may require proper mixing, some cells may not. So based on which you can choose the optimal bioreactor. Then mode of operation means whether you want to conduct it in a batch or a continuous or a fed batch process. So that terms were familiar to you. So mode of operation of the bioreactor, that also need to be considered while selecting a proper bioreactor. Now there we come to the requirements of a bioreactor. To design and the design and construction of biochemical reactors must exclude such a foreign contamination or preclude foreign contamination. So that means we have to ensure sterility. It should be able to operate under aseptic conditions for a specific time. Maybe a reactor may run for 4 or 5 days. So in that case, up to that specific time, the reactor should ensure sterility. So that's the first demand. Then optimal mixing or aeration with a low uniform shear is required. That aeration or agitation, the mixing or agitation that is given in the reactor should not shear or break the cells. So a uniform shearing throughout the column is required, or a uniform agitation is required, and that optimal mixing is another criteria for a bioreactor. And in a CSTR, as you know, there will be a stirrer at the center of the tank, and that stirrer will ensure the proper mixing of the medium. Okay. Then adequate mass transfer of oxygen. We will discuss the heat and mass transfer later. And adequate mass transfer. Mass transfer means supply of oxygen or aeration. That's also required for proper growth. So the aeration is in a bioreactor is the actual mass transfer process, and that needs to be properly addressed. Then power consumption should be low as possible, because in an industrial process, power consumption needs to be minimized, because that will be more economical. Then a system of temperature control should be provided. Usually, such temperature control systems, automated temperature control systems, are nowadays available in bioreactors, where you will have a temperature probe which will detect the temperature of the medium during the fermentation process. And if the temperature increases, it will be automatically adjusted to the set temperature or the desired temperature by controlling the cooling system. There will be cooling pipes or with cooling or cold water, and the temperature and the circulation of that cooling system, or the water in the cooling system, that will be maintained in response to the temperature that is detected in the medium by the probe, and that will be automated, so that temperature control system will ensure that the system is properly cooled and maintained at the desired temperature. So that's about the temperature control system. Also, there should be a pH control system. pH control system, of course, there is a pH probe, and which reads the pH from the medium. And if the pH fluctuates from the desired level, then, or the required level, then either alkali or acid, which is provided with that reactor, so that will be acid base in is there, so that there will be a pH monitor, and the pH monitor will detect the pH, and the acid or base will be supplied to the medium, so that the pH will be maintained at the desired level. So there should be sampling facilities. So intermittent sampling may be required for checking the product quality and the formation of the product, etc. So there should be sampling provisions. Then the vessel should be designed to require the minimal use of labor in operation, that is, and harvesting, then cleaning and maintenance, so etc. will be there. So manual intervention during the operation, that needs to be minimized, so that labor should the vessel and the entire process should be designed in such a way that there should be minimal intervention by or manual handling, like harvesting and cleaning, maintenance, etc. So maximum possible automation should be there, so that manual intervention and subsequent contamination can be minimized. Then the compliance with the design requirements, such as the ability to be sterilized, then simple construction, simple measuring, control, then regulating techniques, scale up, flexibility, then long-term stability, compatibility with downstream processing and anti-foam measures, or addition of anti-foam agents, etc. So all these parameters also needs to be considered while designing such a or selecting such a bioreactor. And it should also follow the different containment regulations. There is a good industrial large-scale practices are there, and that demands different levels of containments, like 1, 2, or 3 biosafety containments should be there, and such industrial strains should or wherever such processes which involve such industrial strains should follow the containment regulation practices based on the level of the containment that is required for the concerned organism. So these are some of the requirements for a bioreactor. Any questions? Hello?
No, sir.
So now we'll come to the different types of bioreactors, and you know that the batch fermenters and continuous fermenters, that concept is already familiar to you. I'm not going to explain that one. That's about the fermentation process. And there are also some recycled reactors. That is, you can see this picture in which there will be a substrate inlet and a product outlet. And this is an immobilized bed of a reactor. Immobilized enzyme system is provided here. And the product out from the product outlet where the utilized medium is taken out, the medium will be recycled back after taking the product, and the medium will be recycled back with its enzyme component, if any. that will be recycled back and fed along with the substrate inlet. So such type of reactors were known as recycle reactors. And anyway, we are not focusing on that one. We are just familiarizing the term with you. Now, uh, there are different types of bioreactors based on its design and technology. Airlift bioreactor is one type. Then there will be tower fermenters, in which bubble column reactors and bubble cap reactors, etc., were coming under the tower fermenters. Then plug flow reactors is another category. Then packed bed reactors, fluidized bed reactors, stirred tank reactors. These are all different types of bioreactors available nowadays. And the CSTR, continuously stirred tank bioreactor, is the popular model that is available in your laboratory and in most of the laboratories where you require such a specific submerged fermentation system. Usually, stirred tank bioreactor is the, or continuously stirred tank bioreactor, CSTR, is the better option. And we also have such a reactor in our laboratory. Now, these are the different types based on the technology that is used. And first of all, I'll come to airlift bioreactor. The airlift bioreactors are similar to bubble column reactors, but they differ by the fact that they contain a draft tube in the center. So this is the draft tube in the center. So this tube is for directing the flow of the air. Okay. So the draft tube is always an inner tube, usually, and this kind of airlift bioreactor is called the airlift reactor with an internal loop. If the draft tube is internal to the reactor, it's placed inside the reactor, then it is known as an airlift reactor with an internal loop. So you can see that the air is actually going up through the internal tube and coming out, and through the sides it will again recirculate back. So this type of airlift reactor is a type of reactor with an internal loop where the tube is placed or our loop tube is placed internally to the reactor so that the air flows through the center of the tube and circulate back. So here in the design, you can see that there is a gas flow inlet and gas distributor through which gas is released. So the gas goes up, and this movement of the gas cycles the medium. So along with the gas movement, the medium will be lifted through this tube, and the medium and the components will be recycled back through the sides. So this agitation or the mixing of the medium is done by the movement of or lifting of the gas from the top to bottom. So the gas will be released through the top. So this is the movement of an internal loop airlift reactor. So this is an actual model of airlift reactor that is shown here. So this is the concept where the air is passing through the internal tube, and along with it, the medium and the product or the components will be lifted and recycled back through the sides, so that that mixing is done by the movement of the air or upward movement of the air. Okay, or an external tube reactor is also possible, where instead of this one, an external tube can also be provided. And such type of reactors were also available. So here you can see that there is an external tube. Okay. So the air is supplied externally. With the airlift bioreactor with an external loop, which improves the circulation and oxygen transfer and decreases shear forces. So instead of internal loop, you can use an external loop, and I will show you another picture of that one. For example, this one. It will lift and external loop. Okay. Instead of an internal loop, it is circulated through an external loop. So this is another model. Now, airlift bioreactors are generally classified as pneumatic reactors. And this slide actually shows the advantages of airlift reactors. So they are also known as pneumatic reactors without any mechanical shearing mechanical steering arrangement for mixing. Usually in CSTR there is an impeller which provides the mixing, but in airlift reactor there is no such provision for mixing or mechanical mixing or stirring of that medium. So the turbulence caused by the fluid flow ensures adequate mixing of the liquid. So the turbulence during the lifting by the air and the fluid flow, it ensures the adequate mixing of that medium. The draft tube is provided in the central section of the reactor, as shown in the previous picture. And the introduction of the fluid, like air or liquid, whatever, causes the upward motion and results in circulatory flow in the entire reactor. And the air or liquid velocities will be low, and hence the energy consumption is also low. Airlift bioreactors can be used for both free and immobilized cell systems. There are very few reports on airlift reactors for metabolite production. And the advantages of airlift reactors are the elimination of attrition effects generally encounters in mechanically agitated reactors. Means the stirring, mechanical stirring may cause many shearing effects on the cells or adverse effects on the cells, which will be minimized in airlift reactors because there is no such mechanical agitation and shearing. It is ideally suited for aerobic cultures since oxygen mass transfer coefficients are high in comparison to sterile reactors because here the entire mixing is done by the oxygen or supplied air itself. So that means these are more suited for aerobic cultures because oxygen supply is better, and that means subsequently oxygen mass transfer coefficients are much high compared to other CSTR reactors in case of airlift reactors. And these bioreactors can be of external or internal loop reactor, as I mentioned. Then advantages for cell culture. That is this is also useful for aerobic systems, and also it is useful for cell culture systems, animal cell culture systems. Then the world's largest industrial fermenter is still ICA is a airlift system first operated in Bellingham, UK, and this UK plant for making single cell protein, and that was made in 1979, and that was the largest industrial fermenter. You can okay, this is the external loop reactor, which is shown here. So this is the largest fermenter. So usually, if you are asked to about the largest bioreactor, certainly it is this. It's not a stir tank reactor, but it is this airlift reactor that is shown here, and this one is the largest one. This picture was actually taken in 78, 10th April 78. That's a, and the dimension is also shown here, 200 feet high and 25 feet diameter. So that's the dimension of this airlift reactor, which is the largest one in the world even nowadays. Okay. Now the next one is tower fermenter. In tower fermenter, elongated non-mechanically stirred fermenter with the aspect ratio of about 6:1. So height diameter aspect ratio of this tower fermenter is about 6:1. And there is a unidirectional flow of gases. There is no recirculation. Gas will flow only through one direction. So there is a substrate will be given from the bottom, and oxygen or air will be supplied from the bottom, and it will raise up, and there will be cooling, heating and cooling jackets. Cooling system is there. And finally, the CO2 after the fermentation will be released on the top. And here is the alcohol out unit. So this is one example of a tower fermenter in which a single direction, a unidirectional flow is provided. There is no downward movement. Always the substrate and the oxygen or the air will go, and it will lift that substrate, and along with the oxygen movement, then it will be lifted to the top. And during the process, during that movement, we have the cooling jackets. which will regulate the temperature at the desired level. And also there is an exit for CO2. After the fermentation, the CO2 will be released from the top. And this entire system is designed in such a way that there's only a unidirectional movement of gases or gases and medium. So there is no downward movement, only upward movement. Used for a continuous production of alcoholic beverages such as lager and ale beers, etc. This tower ferment is an optimal model. Now the next one is about plug flow reactors. Plug flow usually in case of a CSTR or a mixed tank reactor, or a stir tank reactor, you have a medium inlet and a medium or outlet, and also there will be a stirring provision. So the entire content of the medium in this tank will be equally stirred. So the mixing effect is actually in usually means a stirrer tank reactor is usually uh, uniform. So the entire medium is mixed uh, in such a way that there will be a uniform mixing of the medium, and the reaction and all the cells in the medium will have the same environment. Whereas it is important. A very important characteristic of CSTR is that the concentration of the reactants in the outlet is equal to the concentration of the reactants in the vessel. So, what is available in the outlet is the same concentration as that of the reactants in the vessel. So, because it is taken out. So, the concentration that you are taking out is the same concentration as that of the contents of the vessel. So regardless of the concentration of the reactants in the inlet. So that means the CSTR or stir tank systems will have uniform mixing, and that contents of the medium which is available in the tank will be taken out. So the outlet is having the same concentration of reactants as that of the tank. Now, in case of a plug flow reactor, there will be an inlet and outlet, which will be a long tube, and there are various plugs arranged, and in which the substrate is provided. So the medium and this will flow through this tube, and the reaction is actually occurring at the different plugs that is arranged in the tube. So the concentration of the reactions will vary along the pipe. That means from this region to this region, if you are considering, then at different stages of the pipe, there is a different concentration of the reactants. So that means you don't have a uniform reactant concentration as that of a stirrer tank reactor shown here. So the outlet will have another concentration. So it means the substrate or reactant concentration at this point may be high, and this may be high, again low, this may be again low, this may be again low, and when we come to the outlet, we'll have another concentration of the product. So there is no uniform distribution of reactants as that of a stirrer tank reactor in case of a plug flow reactor. So a localized concentrated plugs were arranged, and there will be difference in the concentration of reactants in the plug flow reactor. So plug flow reactors can be modeled as a pipe where the reactants move as a plug along the pipe. So the concentration of the reactants will vary along the pipe, and there is no mixing between and beginning between the beginning and the end of the system. So there is no mixing. So if you provide a plug, for example, you provide some quantity of nutrient growth here with a high concentration of nutrients, that will move as a plug. Now it reaches here, and then you will provide another medium with a low concentration of the substrates. Then that will again move. It will have a different concentration. After some interval, you will again provide some other nutrients, high concentration nutrients, which will act as another plug that will again move. So that means through this tube, localized concentrated plugs will be available. So each plug will have a high concentration of the reactants, whereas in between this region, there will not be any such high concentration. So that can be taken out. So the outlet contains a different concentration than that of the inside of the tube. So that's about the plug flow reactors. Now the next one is a packed bed reactor. The packed bed reactor is or a fixed bed reactors are commonly used for attached biofilms and especially in water engineering or water treatment, etc. So there is a column packed with the enzyme. We provide with the substrate and the product is taken out. So usually it is a attached biofilm or some other enzyme, etc. were packed in the beds of the reactor. So the packed beds are widely used with immobilized cells. So usually the enzymes or the cells with enzymes were packed in the bed. And it is immobilized in the reactor. The immobilized catalyst is packed in the column of a column and fed with the nutrients either from top or bottom. So you can use both directions. Substrate can be fed from top or bottom, and the product will be taken from the other side. So the main point is that the column is packed with the immobilized cells or immobilized enzyme. Okay. One of the disadvantages of packed bed is the changed flow characteristics due to alterations in the bed porosity during operation. So the main issue is that sometimes, since it's a packed bed, if there is some localized formation of some channels during the flow, which results in channeling of that entire contents through that channel. Just for example, some cracks. Say, imagine a condition where some channels with a crack which is created in between, and the medium is flowing through instead of going uniformly flowing through the entire bed. If it is flowing through that already created channels, then that channeling effect will reduce the efficiency of such type of reactor. So if it is not properly maintained, there's a chance of altering the bed porosity and creation of the channels so that uniform flow through that reactor will not be there, and that is a one disadvantage. Okay. In addition, channeling may occur due to turbulence in the bed, and though packed beds belong to a class of plug flow bioreactors in which back mixing is absent. So, in many of the packed beds, slight amount of back mixing occurs, which changes the characteristics of fermentation. So, usually there is no back mixing; it will flow through one direction. But in some cases, some amount of movement of the medium to backside to backward is also possible, and that type of reactors where it can be categorized as a form of plug flow reactors because we provide the medium with substrate at some concentration. Then you can provide a low concentration, and again with some medium with high concentration that will flow, that can flow as a flux. So that type of setting is possible in packed bed reactors. Packed bed reactors also. The next one is about fluidized bed reactors. Fluidized bed reactors are developed for biological systems involving cells as biocatalysts. And there are three phase systems like a solid, gas, or liquid. So these fluidized bed reactors were used with the biocatalysts or the cells and in different phases like solid phase, liquid phase, or gas phase. All the three phases can be used with the biocatalysts like cells. And these fluidized bed reactors are generally operated in concurrent upflow with the liquids as a continuous phase. For example, here we have a substrate provided from the bottom, and here we have the immobilized enzyme as a fluidized bed. So this can be cell also. This immobilized system can be cell also. Now, the product will be taken from the top. Okay. So the movement of a substrate will be from bottom to top, and the reaction will occur in the immobilized bed that is provided here with either uh, cell or enzyme. So that is a biocatalyst. Basically, the particles used in these fluidized bed reactors can be of three different types. So the materials that is packed in this area that are of three types, like inert core on which the biomass is created by cell attachment. So it may be an inert core with the cells were attached. Actual cells were attached, and that biomass is the cell. Then another one, porous particles in which the biocatalyst is entrapped. So on the surface of the inert material, the cells can attach, or the cells can be entrapped in a porous material. So such porous particles and the cells will be entrapped or trapped within the porous material. Instead of attaching, it will be trapped within the porous material which is packed in this one. So the cells or the cells will be trapped within the porous material packed in this bed. And there are other possibilities like cell aggregates or flocks. The cells will self-immobilize by forming flocks or cell aggregates, and that will create the bed. So these are different possibilities, and there are three different types of fluidized bed reactors based on these three different models. In comparison to conventional mechanically stirred reactors, these fluidized bed reactors provide much more lower attrition of solid particles. So that means these reactors will not break the cells uh, or damage the cells compared to other models. Some advantages are there. In comparison to packed bed reactors, fluidized bed reactors can be operated with the smaller size particles without the drawback of clogging and high liquid pressure drop, then channeling and bed compaction. Usually, in the case of previous one, that is a packed bed reactors, there is a possibility of a channeling and drawbacks and clogging and blocking. All these things will be, are possible in case of the previous packed bed reactors, and that results in lower outputs. Whereas in fluidized bed reactors, uh, this can be overcome, like that's a clogging or a pressure drop or channeling and bed compaction, etc. Such type of problems that which is occurring at the packed bed reactors will not be there in case of a fluidized bed reactor. Then smaller particles size facilitates higher mass transfer rates and better mixing. That's another point. Since the particle size in this fluidized bed reactor is small, and it facilitates high mass transfer rates. Usually, uh, small size particles, like even like air uh, air bubbles, smaller air bubbles will provide larger surface area, and better mixing and better aeration is ensured when you are creating smaller bubbles. And we'll discuss that one during the session on mass transfer. Anyway, uh, smaller particle size that facilitates high mass transfer, and also it ensures a better mixing. Then volumetric productivity attained in these fluidized bed reactors is usually higher than in the sterile tank reactors. So overall productivity attained that is also higher when you are comparing it with the packed bed reactors. So when we compare the packed bed and fluidized bed reactors, this will have some more advantage. Fluidized bed reactors will be more advantageous in terms of its better mixing, better volumetric productivity, and more stability towards the backdrops like clogging, channeling, bed compaction. Such problems will be eliminated in fluidized bed. So it can be considered as a better model than that of the packed bed reactor. And the next one is about sterile tank reactor. You already know that, and because even in your degree curriculum, this might be a topic. So these are the different portions of the fluidized, as well as the sterile tank reactor, where you will have an aeration provision with an filtered air inlet. Then there will be a harvest line to take the product out. Then there is a cooling system with the cold water inlet, and a temperature control probe will sense the temperature, and accordingly the cooling system will adjust the temperature. Then there is a cold water jacket that is shown here, and cold water outlet, cold water inlet. Okay. Then this is the impeller with a motor which ensures the steering. Then there will be an inoculum port. Then also steam inlet and food inlet. Steam inlet actually which is required for sterilizing the tank. Then pH control for detecting and monitoring the pH, and also this pH control and reservoir of acid-base reservoir will be there, in which the pH is detected, and accordingly the acid or base will be added to adjust the pH to the desired level. So these are all different components of a stir tank fermenter or a CSTO. So I think you already know that concept. So this is about some of the models of the large fermenters, CSTR models. So any questions? Hello.